Okay. Okay. Thank you very much. And now you can.
Okay, great.
Could you speak a little bit slowly?
Oh, yes. Okay.
More slowly. Okay.
Sorry
Thank
about
you very
that.
much.
Yes, thank you for your patience. So my name is Nicole. I'm currently a postdoctoral scholar, and today it's an honor to talk about the ethics of my PhD work as a scientist and engineer. So in the animal kingdom, invertebrates make up 97% of all species. And invertebrate research has really been the backbone of scientific experiments. So research using model organisms like the ones shown here have broader impacts in basic biology, ecology, and even human health and medicine, as shown with the previous presentation. But invertebrate research is largely unregulated and is often justified as more ethical than research using higher order animals, including vertebrates, although recently this trend is starting to change. So people are paying more attention to the ethics of invertebrate animals, and shown here are two recent examples from earlier this year that extends more protections to cephalopods, like octopuses, and decapods, like lobsters and crabs. So to ensure animal welfare in research, there are expert committees and organizations with ethical guidelines. So in the US, where I conduct research, there's the IACUC, as shown here, which oversees animal care and use. And these committees typically have vets, animal scientists, bioethicists, and other non-scientific members. But they typically don't oversee invertebrates like cephalopods and decapods shown here. Even those guidelines on cephalopods are really recommendations and not enforced regulations. So the EU and countries like Australia do have some protective legislation over invertebrates, such as the Australian Code of Practice, which then examines 4 different aspects of animal research: well-being, stress, distress, and pain. Pain is defined as an unpleasant sensory or emotional experience associated with actual or potential tissue damage. It is a central, not peripheral system, so it requires a centralized nervous system as well as some level of sentience. In contrast, nociception is an objective physiological response to noxious stimuli that cause or potentially cause tissue damage. And this excludes subjective experiences such as unpleasant sensations or emotions. So nociception is just sensory information about the state of the tissue, which is different from pain as perception. And some lower order animals do not have nociceptors or even nociceptive responses. So one species of invertebrate that does not have nociceptors and is not protected under any regulatory council is the moon jellyfish, or Aurelia aurita. And that's the model organism that I've used in my work. So to summarize, in my PhD, I built a biohybrid robotic jellyfish, or an augmented jellyfish, which is a combination of live Aurelia aurita, as well as an embedded microelectronic system to control their swimming. This is an example video that shows the augmented jellyfish swimming off the coast of Massachusetts. We carefully monitored the animals used in these field experiments, and I'll go over the design and experimental setup after giving a broad background. So the motivation behind this research is, and what I like to explain in my scientific presentations, is to expand our current capabilities to monitor the ocean. So even though we know that the ocean is important for processes like regulating the climate, modulating oxygen and carbon dioxide, and providing food, medicine, and transportation, we really only know, literally and figuratively, a drop in the ocean. And the current tools that we have for monitoring the ocean include remotely operated vehicles and autonomous underwater vehicles. These have really great advantages, but many of these technologies are still limited. The disadvantages include being costly, bulky, consuming high power, and leaving larger vehicle wakes. So as an additional tool, we can look to nature for inspiration to build bio-inspired aquatic vehicles. And these can approach more delicate areas of the ocean, like among coral reefs. So in particular, jellyfish are a great model organism because of their high energy efficiency, which is one of the main challenges in robotics. So within bio-inspired design, there is a spectrum of different approaches. And on one end of the spectrum is a purely mechanical robot, which does not have any issues with animal ethics, but they often require a lot of power. On the other end are more of these biological constructs as shown here, and there are some ethical considerations with using animal tissues, but the main limitation here is that they can only survive in limited environments in the lab. And so the approach that I'm talking about today is to use live jellyfish as well as a microelectronic system to control their swimming. And this has certain advantages because it's low power and low cost. And because these jellyfish are found in these different areas in the ocean, they're also adaptable to many environments. So our rationale for this research is that jellyfish are very energy efficient, and using alternatives like completely engineered robots still doesn't address some of the grand challenges of robotics. So this is a multidisciplinary project with applications in biology by understanding how jellyfish swim, as well as in robotics by using this biohybrid technique, and also in oceanography for applications towards tracking climate change. It's also important to note that this species of jellyfish is a cyphozoa, which do not possess nociceptors or pain receptors. And cyphozoa also have a very diffuse organization of nerves, even when compared to other types of jellyfish. So because of the lack of mechanisms for pain or nociception, we can use stress responses like mucus secretion, which is a defense mechanism from external stimulation. But this also occurs with normal behaviors like feeding, reproducing, and modulating immunity. So stress is only apparent on a molecular level, from proteomic, metabolomic, and transcriptomic analyses, not behavior. So our augmented jellyfish includes a live Aurelia aurita, as shown here, as well as a robotic system that's embedded. So I do want to say that even though we embed this electronic system, which has a wooden pin here in the center of this animal, I did test a variety of adhesives and found that superficial glues were more difficult to handle and actually caused more tissue damage afterwards. Whereas with our design, this pin, the animals had a few small pinholes that healed within a day after removal. And these animals are very fast healers and generally return to normal behaviors afterwards. So this is a video of how we embed the electrodes into smaller adult jellyfish. This is just a visual representation, but we conducted all of our work on larger animals. Our major experiments included free swimming experiments in the lab, as shown on the left, using 6 individual animals, and a similar setup on the right in the field using 4 animals. And this determines how externally controlled swimming frequencies affects jellyfish swimming speeds. But the main idea in our experiments is that it's the first step to eventually attaching sensors to jellyfish and sending these out into ocean environments to collect data for monitoring. We were able to demonstrate increased swimming speeds up to 3 times faster than their baseline in both the lab and the field. And these augmented animals used 10 to 1,000 times less power per mass than existing swimming robots. So for more information, you can visit the papers at these QR codes. So our main ethical considerations are categorized into 5 parts: welfare interests, dignity or integrity interests, wisdom of repugnance, presumption of restraint, and environmental impacts. We also wanted to consider the jellyfish as individuals, as well as a species, and as influencing the environment and ecology on a broader level. So first, I want to highlight the public perception of our work. In almost every scientific presentation or media interview about my work, I've been asked about whether this harms the jellyfish. I've also gotten quite strong reactions about how modifying jellyfish is wrong, regardless of any defenses. And to that, I want to discuss the wisdom of repugnance or yuck factor, in which intuitive negative responses are interpreted as a sign of harm or evil. So in particular, Cass states that reflexive revulsion shows the intrinsic morality of experiments, like with human cloning. But critics say that this is built upon prejudices and actually warrants more examination. There are previous studies of invertebrates that I'd like to highlight here. So first, less controversial work. Here is a biohybrid sea slug robot on the left, which incorporates live sea slug tissues, and even biological work on this species of jellyfish, as shown on the right, by cutting them into halves or quarters and observing them resymmetrize into circular shapes. So these cut pieces of jellyfish were able to exist and survive as individuals. And neither of these received much public criticism for their ethics. But in contrast, RoboRoach, which is this electronic product that you can buy to embed and control cockroach motion, which is very similar to augmenting jellyfish, has received criticism. They've published an ethics page to address some of these critiques, and it seems like both RoboRoach and modified jellyfish share the same wisdom of repugnance by the public. There's also this concern that we're playing God, both for animal welfare issues and as a slippery slope if this work escalates into higher order animals. But of course, there are committees to guide work on those animals. And so for our purposes, we'll proceed with focusing on our experiments with jellyfish. Regarding welfare interests, and if jellyfish even have welfare interests that can be harmed through experiments, the scientific consensus is that jellyfish do not have sentience or pain because of their distributed nervous systems and lack of nociceptors. This is also supported by the question of whether jellyfish even have a sense of self, because those halves or quarters of jellyfish can survive independently as individuals. Other researchers have shown this in a series of excision experiments, as shown here, but we still wanted to err on the side of caution using both the precautionary and minimization principles. We also applied the 4 R's, which applies to the animals as individuals. So with reduction, we wanted to minimize the number of animals used to answer scientific questions. And actually, there's a very interesting discussion by Tannenbaum using a rights-based view instead of utilitarian. So out of fairness to individual animals, he suggests that researchers actually use more animals to minimize the cost to an individual animal. So we used 6 animals for the lab experiments and 4 for the field experiments, which is enough for statistical analysis. And we did make sure to allow the individual animals to rest and have extra food before and after. With replacement, using alternatives to animals when possible, we also developed a theoretical model of jellyfish swimming that showed good agreement with our experimental work, but we still needed to conduct these animal experiments to validate the models. But in the future, we'd like to use the model more and experiments less. With refinement, procedural changes to minimize the pain, suffering, and distress, again, we did allow the animals to rest and fed them extra before and after, and our experiments were relatively short, so less than a few hours long. The animal behavior also returned to their baseline after we removed the devices, and the animals were even reproducing in the tanks during this time. With scientific reproducibility, we wanted to justify these experiments with strong data and scientific rigor. And I believe that our research has broad applications in biology, robotics, and environmental science. We were also careful to monitor their mucus secretions, which occurs normally when the animals are touched, but we did not perform any tests to see if the animals were stressed on a molecular basis. And this is work that we want to do in the future for future animal experiments. To consider modifying jellyfish as a species, augmenting jellyfish does have implications for the welfare of the species as a whole. There's this open question of whether artifices affect their feeding, their lifetime, and reproduction, which can then affect their evolutionary fitness. But because our tests have been limited to a few hours, whether this is relevant to the species is still unknown. And I should also note that the species has been considered invasive before, and the overpopulation of jellyfish blooms has negative impacts on the environment. So blooms are affected by factors that are natural as well as anthropogenic and climate change, but jellyfish are very fit, likely due to their multi-phase life cycle, which has both a sexual and asexual reproduction phase. So it's unclear if modifying just the adult forms will do anything to the jellyfish on a species level. And even if it hypothetically does decrease their fitness, is their species level welfare even relevant if they're considered a nuisance? And finally, I think the biggest open questions are the potential impacts to the environment and ecology, which feeds into the idea of stewardship. So as future tools for ocean monitoring, possible issues include plastic waste and electronic waste from the devices, and if other animals ingest these components. So we do want to incorporate using more environmentally friendly materials like biodegradable electronics and plastics, but this is still an open question because our current technology just isn't at this level yet. But we do want to be conscious about these issues beforehand. And in the field tests, so the tests in the ocean, we were careful to make sure that we didn't leave any components behind. So for future work with augmented jellyfish, we do want to continue applying the minimization and precautionary principles and think about the 4 R's and incorporate tools that we haven't used before, like molecular stress markers and longer-term tests. So participating in ethical discussions like this is also very important so that it will be necessary to address all of these open questions about deploying these jellyfish in the ocean in the future. So with that, I'd like to thank you all for your time and patience with the translations and to acknowledge the people who made this work possible. So thank you to my PhD advisor, John DeBeery, our ethics co-authors from Stanford, Drs. Lenk-Zuska, Wheaton, and Federico, and thank you to our advisors at the Benchside Ethics Consultation Service provided by the Stanford Center for Biomedical Ethics. If you'd like to read an expanded version of these ethical points, you can visit the QR code here. So thank you very much.